Let's talk about some chemistry of hydrogen. So you know all about protons, you know all about hydride, possibly. Now, if you have a hydrogen atom is simply a proton and an electron, and you represent that. It's essentially a hydrogen atom is a radical species, it's an unpaired electron. And that unpaired electron can be lost, which would give us a proton, simply an H+ species, a proton with nothing in the surrounding, or no electrons surrounding that proton. Or the other form of chemistry of hydrogen is that it can gain an electron. And if hydrogen gains an electron, it now has 2 electrons in its outer shell, which is a full 1s outer shell, will give it the same outer shell electron count as a helium atom. And that would be a hydride species. So hydrogen is a special atom, where it only has 1 electron, so it can lose that electron to become a cationic species or gain an electron to become an anionic species. And there's a chemistry of protic compounds and a chemistry of hydridic compounds for us to look at. Now, a naked proton surrounded by nothing cannot exist. It will always exist in combination with something else. Because if you think about it, a proton is a very, very potent Lewis acid. It is, if you like, the ultimate Lewis acidic species. Just a proton with no electrons around it cannot exist in chemistry. So although it associates with various molecules and we have an important chemistry of species bonded to the proton, it is worth stating that a naked proton can never exist in chemistry. So if you have an acid solution, then you do not have naked protons swishing around in your water solution. What you have are protons associated with water molecules. So a proton is a Lewis acid, a water molecule is a Lewis base. You get the H+ adding to the H2O, and what you actually have in solution is an H3O+ species. Now, electronegativity difference between atoms allows us to predict the polarity of bonds in covalent molecules. And it allows us to predict the polarity of bonds in molecules containing hydrogen. Molecules containing hydrogen might be delta+ on the hydrogen, and they might be delta- on the hydrogen. And the only way we can tell is by comparing the electronegativity of hydrogen to the electronegativity of the atom to which it's bonded. So, if it's partially positive charge on hydrogen, then we call it a protic substance. If it's partially negatively charged, we call it a hydridic substance. Let's look at a table of electronegativities. Hydrogen, with a Pauling value of 2.20, is right bang in the middle. Hydrogen is going to fit somewhere here in the middle of the electronegativity series. And that means that if hydrogen is in combination with an element on the left of the periodic table, then it's going to form what's known as a salt-like metal hydride. The electronegativity of hydrogen is much higher than the electronegativity of lithium. So if you combine lithium and hydrogen, you will produce something called lithium hydride. And lithium hydride is so polarized, it's essentially a salt with lithium cations and hydride anions. If you react hydrogen with a molecule or with an atom which is in the middle of the periodic table, so let's take as an example carbon. The electronegativities of carbon and hydrogen are quite similar. Carbon is slightly more electronegative than hydrogen, but only slightly more. So you could predict a polarity of this bond, but you would also probably tell me it's not going to be very polar. And when you have a situation like that, you have a very covalent bond. So if the electronegativities are similar, those are highly covalent bonds. Now, if we take something like fluorine, which is extremely electronegative, so it has very high electronegativity, and combine that with a proton, then you will produce HF, hydrogen fluoride. The fluoride is the negatively polarized part, and the hydrogen is the positively polarized part. So we can predict what sort of compounds of hydrogen we're going to get simply by where its partner atom is in the periodic table. So you can have hydrogen with a 1s2 hydride electron configuration. There it's said to be in a formal oxidation state of -1. You can have a hydrogen atom, of course. Anything in its elemental form has an oxidation number, or an oxidation state of 0. So we have a 1s1 configuration. And we can pull that electron off and produce protons, and then you see hydrogen in an oxidation state of +1.